So, back at it. 1 day equals 24 hours. 1 hour equals how many minutes? 60. How many minutes are in a second? Sorry, how many seconds are in a minute? 60. So I have three qualities I have to use to get to my final answer. Now, unless I'm able to calculate from my periodic table, and it's not one of the five we had to memorize, megagrams, kilograms, grams, centigrams, milligrams, I'm going to have to, these I had to memorize. I will be able to calculate the amount of grams from the periodic table for my elements and compounds. But these ones you use on a daily basis. We live our lives through days broken up in 24 hours, and hours broken up in 60 minutes. 1 minute's broken up in 60 seconds. 3.45 days. Put that over a fraction. Which one is, well, I'll use first. I'm going to use day first. 1 day holds 24 hours. I'm not in seconds yet. 1 hour holds 60 minutes. 1 minute holds 60 seconds. If I go back, I cross out all of my, what's the numerator and denominator. Days get crossed out, hours get crossed out, minutes get crossed out, leaving my only unit, seconds. So if I rewrite this, 3.45 times 24 times 60 times 60 divided by 1 times 1 times 1. Hell, one more times 1. Put my handy dandy calculator. 3.45 times 24 times 60 times 60. I get a final answer of, using 3 sig figs, as my question started off with 3 sig figs, 1, 2, 3, 298,000, or I could have wrote it as 2.98 times 10, 1, 2, 3, 4, 5 seconds. You should feel comfortable doing that type of fractions. If not, you need to spend some time after school. You need to come to me during your nest. We will not be going back and spending a day or two doing dimensional analysis. This was it. If you're not where I need you to be, you need to get where I need you to be. So, like I said, talking about the mold background, it wasn't until the 90s where we were able to see molecules. With electron microscopes, we began to start to see the outline of molecules. And it wasn't until 5 years ago where we were able to actually photograph individual electron clouds. Cornell University did a very interesting experiment in 2021 where they were able to isolate crystallized and examine the crystallized structure of a certain type of combination, and I'll throw a picture on of what they recorded in a little bit. But under 1,000,000 times magnification, they began to see the outer shell of our atoms. We have known about atoms since the 1800s. Dalton was our first one to give his postulates, telling us about what atoms are. Remember his indivisible ball. It wasn't until the turn of the last century that we start seeing electrons as both being a particle and a wavelength. Two different principles tied together. atoms are incredibly tiny and are impossible for us to count them individually. If we just took the atoms, counted the atoms of a single paperclip of iron, it would come out to be roughly around 6.38 times 10 to the 23 atoms. So you're talking about number 6, 3, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 zeros behind it. That's how many atoms we can roughly measure in one paperclip. I think right now the current population of this planet is around 8 billion. 1,000, million, billion. Right there is the number of humans estimated as currently walking this planet. It's higher now, but I think around last year or the turn of this year, the average amount of humans possibly walking on this planet was 8+ billion of us. There is a magnitude more of atoms found in a paperclip than there are humans walking this planet. Just to give you an idea of how many there has to be. The mass of one atom, the AMU, the average mass number, can be calculated looking at the periodic table. So if I take a look at a periodic table, your AMU, your AMU, that's going to be your average, that's going to be your atomic mass number right here. Because remember, we broke this down. There are two main numbers on the periodic table that we had to know. Our top number, that was our atomic number. That told us how many protons were present. The bottom number at the bottom of the box tells me its weight, its mass. So we're pulling stuff from previous. Precious, up. Go for it. Make sure you sign out for me. Now we break it down and we try to measure the mass of just one atom. We're going to get to this 1.66 times 10 to the negative 24. So in front of this 1, there are 23 zeros. Incredibly small to measure individually. So, to make it easy on ourselves as scientists, we're going to measure. We discovered that if we measure the molar mass of an element, it's going to equal 6.022 times 10 to the 23 atoms. And that's what we're going to work on today. So, what is my big takeaway from the previous item? My mole is my link between grams and atoms. When I want to measure how many atoms I need, how many atoms of something I need to put it in a unit I can easily measure. Grams is our normal measurement for weight. Our mole is used to measure a group of atoms. Think of it as like a dozen of eggs, or a dozen of something. If I go to the bakery and I say I want a dozen donuts, how many donuts am I getting? If I say I need a dozen eggs, how many eggs am I getting? How many eggs are in a dozen of eggs? 12. Say I need 2 dozen of eggs, how many eggs am I getting? 24. I need a half dozen of donuts. How many donuts am I getting? Perfect. The only difference now is I want you to attach mole, not to this little creature here, but to 6.022 times 10 to 23 atoms. Same idea. It's just a unit that we're going to use to measure stuff in. So this isn't in your notes. This is a copy from your slides here. But I pulled iron. Iron's a really cool metal. I harp on it a lot. Iron is the first death nail in our stars. It's the first element in its development that requires an endothermic reaction, meaning that steals heat from the star that's currently being built in. The very metal that allows you to exist as a multicellular organism is the first death note of the star it was forged in. There's some poetry in that. But, like I said, my top number, that's going to be my atomic number. That tells me what? Number of what in my atom? Number of protons. My atomic mass number on the bottom here. It's going to tell me this number right here, 55.85, like we calculated earlier, equals 6.022 times 10 to the 23 atoms of iron. That equals 1 mole of iron. 6.022 times 10 to the 23 is my dozen for atoms. And I can look at my periodic table and figure out how many grams I need of an element to get 6.022 times 10 to the 23 atoms. If I looked at another item, if I looked at hydrogen, I need 1.01 grams of hydrogen to get 6.022 times 10 to the 23 atoms. If I ask for how many grams are in 1 mole of boron, 10.81 grams of boron equal 1 mole of boron. They're interchangeable. So I know that we don't have the whiteboards out, so I'm going to skip to the next slide. I'm going to go straight to the coursework. Because we're not doing the examples, I want to do 1 or 2 of them with you. So this is on top of your page. I just copied and pasted it over. What do I do with that periodic table? Here we go. So if I'm looking at the example up top, aluminum. 1 mole of aluminum will hold 6.022 times 10 to the 23 atoms. And I need 26.98 grams of aluminum to get that many atoms. Let's do calcium together, and I'll have you do the other ones by yourself. For calcium, how many atoms will fit into 1 mole of calcium? Give you a hint, you're already staring at it. 6.022 times 10 to the 23 atoms will hold 1 mole. How many grams of calcium do I need to get 1 mole of calcium? 40.8. 40.08. Where did I get that? I pulled it straight from my periodic table. Since when I moved the screen, it gave me a lot of issues, I'm going to leave this screen up and I'll put a timer on for 5 minutes. When the music ends, we'll move on together. But I want you to figure out sulfur, magnesium, copper, and lead.
We took moles all the same.
Yeah, like a dozen of something's always the same, right?
Yeah. I was checking.
There you go. You got it. That's it. That's it. That is the man behind the curtain. If we want to take it to a Wizard of Oz connection, allegory. Don't mind the man behind the curtain.
Mr. Webster. What's our list today?
What's that?
What's the list today?
4G. Tomorrow's advisory. Whether I'm looking at donuts, I'm looking at yeah, that's fine. If I'm looking at donuts, I'm looking at hold on. Potatoes mean haters. Eggs, same thing. I said when it doesn't have something, I want a dozen pens. I want a dozen papers. I want a dozen students. I want a dozen paper clips. It's always the same. White teacher, and I'm also a head coach for the team. I'm going to teach social studies now. That's the stereotype. All white ball teachers teach social studies. Head coaches.
Yeah, why'd you go bald? Why'd you bald yourself?
Because it was falling out. You know, this spot back here where it wasn't growing, and up here it's getting real thin. So it's like I can either just accept fate and clean it all up, see what it's going to look like for the rest of my life, or I sit there and do this weird thing where I start curling over one of the sides, trying to hold on to some vitality or dream that I still have it because I'm getting old.
What grandpa is that?
Oh,
Sorry.
I'm sorry.
Oh, I'm sorry. Well, if it makes you feel better, you look great.
Thank you. I appreciate it. By the looks of it, we all got this done. So I'm going to pause on the video, pause on the timer.
It does look good.
I agree. I thank you. So, like I said, number of atoms in something is always going to be this number. It's aggregate. It's a number. This number also has a name, Avogadro's number. Avogadro was a Greek philosopher, and when they discovered the number, they because he had done work with atoms all the way back in the BC era, they attributed a number to him. Not something you need to worry about on a test, but just kind of a curious thing if you ever want to know where that number came from. Sulfur. If I'm looking at sulfur, how many grams of sulfur do I need to get 1 mole?
32.07.
3207. If I'm looking at magnesium, how many grams is going to hold 6.022 times 10 to the 23rd power of atoms? 24.31. Where am I getting these magical numbers? Straight from the periodic table. The atomic mass. If I'm looking at lead, in order to get 1 mole of lead, I need 207.2 grams. To get 6.022 times 10 to the 23 power of atoms of copper, I need to weigh out 63.55 grams of copper. Number of atoms always stay the same. The grams of the elements, what's going to change. Keep that in mind. Because we can take this looking at the second part of our questions. So, I forget why I wrote this back out, but I wrote out our steps for our dimensional analysis because on the bottom part and what remains, what you guys are going to do for the rest for homework, these are qualities that allow you to make conversions between moles, atoms, and grams, just like you did when you converted between metric or time units. When I say I had 10 centigrams of something and I need them in kilograms or megagrams or milligrams. I'm going to follow the exact same steps, and I pulled them straight from the 3 steps right from your worksheet. Number 1, write out your equalities, your equivalent relationships. Choose the number that goes to the units that you want. Copy everything down. Multiply by the fraction. Remember the units you have to go on the bottom. The units you have go to the bottom, and the units that you want go on the top. So whatever I have up top, whatever unit that is, has to be the same unit on the bottom for the next one. We just back and forth until I get whatever I want. If I start with X and I want A, and I say X equals Y, Y equals Z, Z equals A, back and forth until I have Z over A. Whatever I'm getting rid of goes on the bottom. Whatever I want stays up top. So I'm going to skip this one. Do I have creations, whiteboards? Let's do one from the homework. So, let me go check the door first. So I give you an example, making sure we understand we can cancel out those units. Let's look at number 1 together, and what you'll do is you do the back for homework. Sound good? All right. And by the looks of it, you'll have a little bit of time to go in and start on it because we got 18 minutes till the bell rings anyway. All right. So I have 89.6 grams of calcium, and I need that to equal 1 mole. Try to figure out how many moles of calcium exist in 89.6 grams. So, I need my equality. Now I know 1 mole calcium equals how many atoms? How many atoms of calcium do I need to get 1 mole of calcium? 6.022 times 10 to the 23 atoms. Now, I may not need that equality, but I need to know what it is. Six point 0.022 times 10 to the 23 atoms of calcium equals how many grams of calcium? 40.08. Where did I get that 40.08? Right from my periodic table. So, I have grams, 89.6 grams Ca. Put that over a fraction to make my life easy. Which equality am I going to use? Really, I can also write this out as 1 mole Ca equals 40.08 grams. Because they all equal the same. If I change it up and put up here, 1 mole Ca equals 6.022 times 10 to 23 atoms. Ca, which also equals 40.08 grams Ca. I really only need 1 fraction. What's my fraction going to be? What am I going to have on top? So if my next fraction is this, what can I put on top? Am I going to put moles, atoms, or grams? Moles, right? Moles is what I want. 1 mole Ca. What's going to be in the bottom of my fraction? We already did moles, so it's going to be the number of atoms or number of grams? Number of grams. 40.08 grams Ca. Gram Ca are going to cancel each other out, leaving my only unit, moles Ca. Nice thing, my ones cancel each other out, so it just becomes on 89.6 divided by 40.08. Someone tell me what that answer is. In the proper amount of sig figs. How many sig figs is your answer going to be in? 1, 2, 3, 4, 5. 3. .24 mole plus calcium. 1, 2, 3. There's my my rounding line. I have a 5 on the other side of it. Therefore, my 3 becomes a 4. And that's my answer. You guys are going to do the back for homework. We got 14 minutes till the bell rings. I'm going to be around to talk to you. I want you to give him a shot. I need you to have your answers. I need you to have your work in those equality fractions. If it's not in the equality fractions, I can't justify to myself that you did it the right way. Because this is what we're doing. This is what I showed you. If you start off every question writing out the moles of whatever's there, equals the amount of atoms, equals the atomic mass of your element, you're going to be in good shape. So if I'm looking at number 2, I'm looking at S. What element's S? Sulfur. 1 mole of sulfur equals Avogadro's number, 6.22 times 10 to the 23 atoms, S, equals the weight, 32.07 grams, S. If you do that for each one, you have all the equalities you could possibly need for each question. All these numbers mean the exact same. If I weighed out 6.022 times 10 to the 3 atoms, I'll get 32.7 grams of sulfur. 32.07 grams of sulfur is equivalent to 1 mole of sulfur. 1 mole of sulfur has 6.022 times 10 to the 23 atoms of sulfur in it. All these numbers mean the same to each other. We're changing how we look at the number. That's all we're doing in dimensional analysis. If you write out this equality each time, 1 mole equals how many atoms, equals what the amount of that equals the grams of that element, you're going to be in great shape. And the best part about it, the first 2, you don't have to even look up. 1 mole is always going to equal 6.022 times 10 to the 23 atoms. Whether I'm looking at sulfur, whether I'm looking at whether I'm looking at, let's pick another one, tin. Whether I'm looking at compounds, we're going to see next time. 1 mole of calcium chloride. That's also going to equal 6.022 times 10 to the 23 atoms. Whether I'm looking at, let's pick a 1 mole of dinitrogen oxide will also equal 6.022 times 10 to the 23 atoms.
Oh, okay.
The mole and the amount of atoms always are the same. What's different is how much I have to weigh to get to that many atoms. The difference is what I have to weigh to get to that many moles. The elements are simple. It's whatever's on the periodic table. When I see you Thursday, today's Tuesday, I'm going to show you how we figure out how many grams are in calcium chloride. We're going to see how many grams are in dinitrogen oxide, monoxide. The first step is we have to attach 1 mole of an element holds 6.022 times 10 to the 23 atoms. And if I weighed that out, it's the atomic mass on my periodic table for that element. If we get that today, you're going to make your life so much easier for the rest of this unit. We just understand this equality right here. 1 mole equals 6.022 times 10 to the 23 atoms equals the atomic mass on my periodic table.
Yeah.
If we get that today, like I said, boom. You've done most of the heavy lifting that we're going to have this unit. The other heavy lifting is going back and reminding yourself what dimensional analysis is. After this, everything's a cakewalk when it comes to dimensional analysis. We get to empirical formulas, we're going to hit a little bit of a road bump, which is fine. I expect that to happen. But that's not going to be to next week, middle of next week. Today, it's our understanding of these 3 items being attached to each other. When I see you Thursday, I'm going to show you how you calculate molecular weight, the mass of calcium, which is 40.08. 5.4. If you want to know what 1 mole of calcium chloride equals 110.98 grams calcium chloride. We're gonna find out. We're gonna figure out how we do that next time. And all of this ties back. If you can add stuff, subtract stuff, multiply stuff, divide stuff, you're in the right place. If you don't know how to do those, we got a little bit of work to do. But if you know how to add things together, subtract things together, multiply things together, divide things together, you're in the right place.
Could you check to make sure I set it up right, please?
Yeah.
That's good?
Mm-hmm.
Okay. So we're also confused on how to get the caret symbol because it's not physically on here.
So you don't want to use the caret symbol. Remember, let me hit clear on this. Say I want to type in 6.0 times 10 to the 23. Because your caret symbol is technically right here. So if I did 6.022 times 10 times 10 caret 23, I'll get the right answer. I'll get that. But let's say I need to multiply that. So I do, if I did that with this right here, 9.6. Let's say I need to find out the moles for that, so I divide that by 6.022 times 10 to 23. I've now, instead of having one number, I've now told my calculator there are 2 numbers in the denominator, and I'm going to get the wrong answer. When you are using your graphing calculator and you're trying to do that times 10 to the 23, all you need to do is 6.022 022, the shift button, the yellow button, and the little column button here for double E. That E represents times 10 to an exponent. You type in what an exponent is, 2, 3. Because if you do it the other way using the caret, that means you have to put 6.022 times 10 to 23 in parentheses. You're going to make mistakes. We've already envisioned that this mistake was going to happen because you're not the first person to make it. That's why we have the E function. Use the E function. Manuel, what's up? Today I'll be at school today, yes.
No, the first
Yeah, I'll be here.
Why?
Jackson.
Whatever you name it. That's great.
Test grades are already posted. So if you go